You are welcome to FANOC Research Group YouTube channel. Please click on the subscribe button to subscribe to our YouTube channel. You will get notified whenever new video is uploaded. Thank you.
So we go straight to the topic for today, sequences in metric spaces. In metric spaces. So, of course, it's not strange. The concept of a sequence is well known to us. And so, we studied sequences in real analysis. That's sequences in R. If you recall, R, if you have xn, and you say that xn is a sequence, you are talking about a function that has the domain as the natural number system and has R as the range. And so if you talk of sequences in R, these are functions taking the domain. Of course, you can talk of the first term of the sequence corresponding with the first term of the natural number system. So which x1, the second term x2, x3. We named examples of sequences in R. For instance, you have 1 over R, 1 over n. Of course, 1 over n n greater than or equal to 1, which is the entire natural number system. If you want to explicitly state the terms, when n is 1, that's 1 over 1, 1 over 2, 1 over 3, 1 over 4. And of course, because n itself cannot be exhausted, you never can exhaust the terms of this sequence. So we studied all this. And if you recall, we even studied convergence of sequences in R. For instance, we said that the limit of this sequence is 0. And what does it mean? If you claim the limit of this sequence is 0, what that means is that given epsilon greater than 0, you can always find a natural number which will depend on epsilon you picked, such that you have that the modulus of xn minus what you claim to be your limit for this particular case is 0. So but let's call it xr, which is the limit, okay, less than epsilon. And this will happen for every n greater than or equal to n epsilon. This is what we mean by convergence of sequences in R. Okay, we studied all those. But this time around, in metric spaces, my structure will not be R. My structure will be a metric space, X, comma, D. So you are replacing R with a space. You are replacing R, which is just the real line, with an arbitrary metric space, arbitrary space. So the structure obviously will differ. Obviously, this structure okay, is a ball or an open interval, if you want to put it. So you need to redefine that structure, the same structure here, balls here, okay, which we have already studied, open balls. Okay, we need to use that to define convergence of sequence and all that. So you see that the topology of the balls with the notations obviously will be generalized in S, D, that's in a metric space. And of course, the structure changes from R to S, D, that's a metric space. So that's what we want to look at, sequences in metric space. So let's share a new slide, and then we formally define what we mean, and then, okay. So let's formally define what we mean. We formally define what we mean by let's definition now. Definition. Let's Xn, of course, the entire natural number system, n greater than or equal to 1, be a sequence. Let Xn be a sequence of points in a metric space. That's the structure, not in R. This a sequence in a metric space, X comma row, X comma D or X comma row, the choice is yours. Now, a point, call that point P in the space. The space is X comma D, a point P in the space X, the metric space, is called a limit point, of a sequence, limit point of a sequence of the sequence. The sequence, we call it xn, okay? The sequence xn, if for every, that's the keyword, for every real number call that real number epsilon, which must be positive. You can always find, so every real number like that, there exists, you can always find a particular positive, integer n, okay, such that all the terms of the sequence can be put inside an arbitrarily open ball. Okay, that's the essence of convergence. I can put all the terms of this sequence inside an arbitrarily open ball. Let me share a new slide and then conclude, and then I will now make some geometrical explanation of that definition of the limit point of a sequence in an abstract metric space. Okay, so if there exists a natural number such, I'm just continuing, we've already seen, such that you have all the terms xn, which is the sequence, can be contained in a ball, open ball, with the radius of the ball is epsilon. Of course, you recall, we defined epsilon before as a positive real number. So, and that's satisfied, that can be chosen as the radius of the ball. Now, center that ball on P, what you call the limit point of the sequence, okay? For all n greater than or equal to the natural number you have picked. So if the sequence xn, if the sequence xn has a limit point which we call P, we say that the sequence xn, converges, to P. That's the point P. And then we write that xn, which is the sequence, converges to P as n approaches infinity. Okay? Alternatively, we can write it that limit as n approaches infinity of the sequence xn is exactly P. Of course, a sequence that is not convergent is divergent. So a divergent sequence is a sequence that is not convergent. So a sequence that is not convergent is divergent. Okay? A sequence that is not convergent is divergent. I need to kind of share another slide, and then I want to make geometrical interpretation of all of this. Okay? Of course, I have a sequence xn. Okay, I claim that P is the limit point of the sequence. If that is the case, then you can always find some epsilon greater than 0, such that that epsilon could be made the radius of a ball, which will now, that ball must center on the what you claim to be the limit point of the sequence, which is P. If that is the case, then all the terms of the sequence will be inside the ball, apart from a finite number, because this will happen for every n greater than or equal to n. Okay? Meaning that from n, n plus 1, n plus 2, n plus 3 to infinity, all of them will be inside this ball. The ones that will be finite, the one that will be outside the ball will be finite. For instance, maybe x1, x2 up to xn minus 1. Those are the ones that will be outside. Okay, so I need to represent this geometrically so that we make more meaning from the geometries of that definition. So what you are saying is that if you have a sequence xn and you claim that xn converges to, say, p as n goes to infinity, what you are simply saying is that if you have any epsilon greater than 0, okay, it follows that for you can always find n which will depend on epsilon, positive also, such that b epsilon on p, okay, that ball, let me rewrite it like this, that is such that xn is in b epsilon p. So that's exactly what convergence means. What that is saying is that, look, if you have, for instance, let me illustrate this. If this is my point P, and I have epsilon minus epsilon, okay, this is the ball, at least in R. You discover that all the terms of the sequence will be inside this ball, apart from finite number like x1, x2, up to here, which will be xn minus 1. Now, up from xn, from this point, xn, of course, xn is capital N because n is greater than or equal to, so xn, then xn plus 1 to infinity, all of them will be, in fact, they will be piling up xn plus 1, xn plus 2, all of them will be piling up at p, as n becomes extremely large, all the terms of the sequence will be piling up at the limit point, which is p. Okay, so that you now see that the terms of the sequence that will be outside this ball, the terms of the sequence outside this ball will can be counted, can be said, okay, it is x1, x2, x3 up to xn minus 1. You can say, well, it is finite, it is just 5 of them, it's just 6 of them, it's just 7 of them, depending on what the sequence is. So you see that all the terms of the sequence will obviously you can't, they will be finite. Okay. Just 1 minute, please. So I'm back. So all the terms of the sequence obviously will be finite, and you can always discover that the ones outside the ball, they are finite. So that's the concept of convergence. I'm going to give examples. So let me share a new slide so we can give example. We've already started okay, so Ruben, you are welcome to the class. So let me share an example. Example now. Okay. Let x comma rho be okay. This is R with the usual metric D. Okay, be a real line with the usual metric and let your sequence now, your xn, okay, your sequence xn n counting from 1 to infinity be the sequence. We know this candidate very well, this sequence very well. Okay. Our claim is that this sequence, which is 1, converges to 0 as n goes to infinity. In other words, 0 is the limit point of this sequence. So that's what we are claiming. Okay. So the solution is that, first of all, we show that 0 is the limit point. 0 is the limit point. We show that 0 is the limit point of that sequence. Limit point of that sequence, which is xn. Okay. Well, let's share a new slide and then we make more sense of such a claim. Okay. Well, you have, for instance, because we are in R, our metric is R comma D. So the real line, of course, you have 0. I'm sure you still remember the sequence we are dealing with, 1 over n. Okay. You have this, the 0 is the limit, so, and epsilon is the radius of the ball. So epsilon is the radius. So center, the ball is an open ball, centered on 0. I'm sure you know that, of course, this is R, the real line. I'm sure you know that in real line, open balls are open intervals. Okay? So if 0 is the center of the ball, the radius is epsilon. To the right, you have plus epsilon. To the left, you have minus epsilon. I'm sure you know, any number to the negative, to 0, left of 0 is negative. So that's minus epsilon. Okay, and of course, you know that the terms of this sequence can be written as, when n is 1, that's 1 over 1. 1 over 1 is 1. 1 over 2. 1 over 3. 1 over 4. This number continues. So let's say this is 0, of course. To the left here, you may have minus 1 here. This is 0. So to the right here, you may have 1. Between 0 and 1, you can have 1 over 2. 1 over 2. You can have 1 over 3 somewhere here. 1 over 3. You see that the terms of the sequence, 1 over 4, the terms of the sequence is approaching 0. So it's approaching zero. It comes as n becomes extremely large. You see that all the terms of this sequence will be piling up at zero. So zero is, of course, the limit point. So if you take a ball, take any ball, okay, at zero, of course, with radius epsilon. So B epsilon, that's the percent with radius epsilon centered on zero. Okay, that's the ball. Now choose your n. Recall that for this to happen, there must be a particular natural number in which n, for all n greater than that n naught, this will happen. So if you now choose an integer n naught such that you have that 1 over n naught is less than epsilon. If, for example, if you have that epsilon is 1 over 100, so you now discover that if you choose n naught, if you choose n naught, for instance, to be 200, you now see that 1 over n naught will be n naught is 200, 1 over 200, okay? And epsilon is 1 over 100. So 1 over 200 obviously is less than 1 over 100, okay, which is epsilon. So in that case, you see that you have the following. I want to share a new slide. I share a new slide. So you see that in that case, that of course n naught, 1 over n naught is 200. So you now see that 1 over n naught, 1 over n naught is less than epsilon. Epsilon itself is 1 over 100. So 1 over 200 obviously is less than 1 over 100. So in that case, we have that the absolute value of 1 over n naught minus 0 is less than epsilon. Okay? So that you now see that 1 over n naught is actually contained, because for this inequality to be obeyed, what's the meaning of that? It then means that 1 over n naught is a term, inside the ball, which is centered on, which is with radius epsilon, which is epsilon is 1 over 100 and centered on 0. Okay? So, of course, you know that if 1 over n naught is less than epsilon, 1 over n naught plus 1, 1 over n naught plus 2, 1 over n naught plus 3, all of them will be less than epsilon. In other words, you have that 1 over n naught is greater than 1 over n naught plus 1, and this is greater than 1 over n naught plus 2, okay? So that you now have, this is greater than 1 over n, of course, greater than 1 over n naught plus 1 is greater than 1 over n naught plus 2. This one is greater than 1 over n naught plus 3, so on and so forth, forming a form of net. So in that case, what can you see? You see that all these terms now, all of them, in fact, beginning from here, all of them, all these will be inside the ball. Okay? All of them will be inside. They are all objects in the ball, open ball with radius epsilon centered on 0. So the only ones that may be outside may be 1 over n naught minus 1. Okay, 1 over n naught minus 2, 1 over n naught minus 2, and so on and so forth up to, 1 over n, n naught, 1 over n naught minus, okay, minus n. So obviously you can count them. There are n of them, actually. There are n of them. There are n of them, okay, in this particular case. So that you now see that all the terms, of course, this one cannot be counted. 1 over n naught plus 1, n naught plus 2, n naught plus 3, and so on and so forth, cannot be counted. All of them are inside this ball, okay? So what that means is that I can put all the terms of the sequence inside the ball, apart from a finite number. These ones are finite. The ones outside this ball are finite. So that is the meaning of convergence of the ball. Okay, so maybe I give another example of a sequence that has a limit point as well, and then we cannot proceed from there. Okay, so I give another example. I give another example. Look at this one. Let xn n greater than or equal to 1 be a constant sequence, okay, contained in a metric space x comma d. Okay, if for example you have that sequence is a constant sequence, such like this one, a constant sequence, k, the terms of the sequence k, just like that. Just like this type of sequence, 1 over, xn to be maybe 2, 2, 2, 2, 2, 2, and so on. This is an example of a constant sequence, k, 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 k. So if you have a constant sequence like this, then our claim is that that type of sequence xn converges to k. Okay, of course, this is easy to show. A constant sequence converges to k. When do we say that a sequence converges? If you can find an epsilon greater than 0, such that what you claim to be the limit point, we contain all the terms of the sequence apart from a finite number. Okay? So let's find a ball, center it on K. Okay? Clearly, you see that any open ball centered at K with any positive radius, which you call epsilon greater than 0. In other words, you have BK with radius epsilon. Okay. In fact, any ball like this already contains K. As a matter of fact, there is no term of the sequence outside this ball, because if you make K the center of the ball, every ball contains it. So interestingly, there is not even a single term outside the ball. That's absolute convergence. So contains, all this ball contains K. So that's convergence. That's an example of convergence of sequences. Okay. Um, maybe I give one more example, then we now go to other concepts. We now go to other concepts. So let me share another slide and then give one more example. Okay. Um, example. Example, show that the sequence xn converges to the number x, okay, in R, which is the real, with the usual metric, with the usual metric. Okay, with the usual metric. Of course, there are two sequences. The first one, A, is that you have xn to be 1 plus 1 over n. Of course, n is positive integer. N is in n. Y, your x, is just number 1. B is that you have xn to be equal to 1 plus minus 1 over n to power n. So this is an oscillatory sequence. Okay. Of course, your n is in the natural number system, and also your x is 1. Okay. Now, well, we want to show that this sequence, okay, converges to x. X is 1. That this sequence converges to 1. We also want to show that this sequence also converges to 1. That's what we want to show. Okay, solution. If you claim that this sequence number A converges to 1, 1 is the limit. So if you claim that it converges to 1 as n goes to infinity, what you are simply saying is that given any epsilon greater than 0, you can actually you want to find a particular natural number, of course, always greater than 0, such that you can put all the terms of the sequence in a ball apart from a finite number. So let me share another slide. Remember, we are just trying to solve, the first one, A. We are trying to solve xn equal to 1 plus n over 1. So we are trying to solve that. Okay, so let me share another slide, and then we now do justice to that. Okay, so so like we said, you have that given epsilon greater than 0, given epsilon greater than 0, epsilon greater than 0, okay, you want to find n greater than 0 such that for all n greater than or equal to, for all n greater than n, you now have that the modulus of the sequence xn minus what you call the limit, which is 1, is actually less than epsilon. So my job is to find this n, okay? There exists n. So I need to find this n. That's my job. If I'm able to do that, then my job is done. But if not, we cannot claim that that sequence converges to 1. I'm sure you recall the sequence itself. Recall xn. Xn, A, the A we are solving. The sequence is 1 plus 1 over n. I'm sure you remember that. So if you now have this, what does that translate? You see that absolute value of xn minus 1 will be absolute value of what? This sequence, 1 plus 1 over n, okay, minus 1, okay, which of course, this and 1, this is just 1 over n, okay? So we show that it show that 1 over n obviously is less than epsilon, okay? For all n greater than n, we have actually that 1 over n, if n is greater than n, if n is greater than n, what's the meaning of that? Then 1 over n is less than 1 over n, okay? So you now see that the absolute value of xn minus 1 is equal to 1 over n, 1 over n, and 1 over n is less than 1 over n. So it's less than 1 over n. And what is this? This one is less than epsilon. If this is less than epsilon, obviously, okay? You now have that 1 over n is less than 1 over n, less than epsilon, okay? So if 1 over n is less than epsilon, you can actually find, look at from here, this one, from 1 over n less than epsilon. If you take the reciprocal of both sides and reverse the inequality, the reciprocal of this side is n over 1. The reciprocal of this is 1 over epsilon. So you now discover that n is greater than 1 over, because if you take reciprocal, you must reverse the inequality. Instead of less, it will be greater than. So n is greater than 1 over epsilon. Okay? To continue, I want to share a new slide. Okay? Now, for all n greater than n, we have that we have xn minus 1, which we have found to be 1 over n, is less than 1 over n. Of course, this is less than this. So what have we shown? We have shown that we've been able to find n. N is greater than, actually, n is greater than 1 over epsilon. 1 over epsilon. Okay? In fact, you can even say n to be uh, equal to the set 1 plus the the you know this is the greatest integer function. Okay, so n can be the whole of this, 1 plus the greatest integer function of this. That actually shows that you have been able to produce n. So having been able to find n, okay, what's the meaning of that then? It follows that xn converges to number 1 as n goes to infinity. Okay? So That is for that case. So having been able to find n, so you can now put all the terms of this sequence inside that ball, and the only ones that are finite are from 1, n1, n2, up to n minus 1. Okay, so that's the proof for that example. We want to show the one for B now, and then B is another sequence. If you recall, B we have, can you remember B? Xn, 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 which is equal to 1 plus minus 1 n over n. Okay, n is positive, that's n belongs to n. And of course, we claim that the limit is 1. So that's all we want to claim. If that is the case, the meaning of that is that given any epsilon greater than 0, you want to find, we want to find in a particular number n, let's call it n1, which will be greater than 0, such that you can put all the terms of the sequence in this ball. Okay, and this will happen for every n greater than n1. Okay, so but we already know what this sequence is now, which is this one. Okay, so if you put it there, that is, you have the absolute value of 1 plus minus 1 to the power n over n. Okay, then minus 1, minus 1. Obviously, 1 and minus 1 will go, leaving you only with this one. So leaving you only with minus 1 to the power n over n, the modulus of that. Of course, if you take the modulus of this, the only one that will be affected will be these numbers are natural numbers, so they are already positive. The modulo, the absolute value will only turn every negativity into positivity. So it will affect the denominator, which is minus 1. Minus 1 to the power n will simply be 1. Okay, for all n. Will obviously be 1 for all n. So this will translate to the following. This will translate to the following. So that would be equal to 1 over n. Meanwhile, we have already studied this, just like in example A. Okay, we've already studied it in example A. So, and if we choose, we can choose now, like we did in A, we can choose n1 to be greater than 1 over epsilon. So if n is greater than or equal to n1, or of course, if n is greater than or equal to n1, it also translates to 1 over n being less than or equal to 1 over n1. Okay? Then you have convergence. You have that xn minus what you claim to be the limit is actually, of course, we have done all this computation. This will be equal to 1 over n. Of course, this is less than 1 over n1. And obviously, this is less than epsilon. How much more is so less than epsilon? Okay. So what have you done? You have just simply shown that xn minus 1 is less than epsilon. And this will happen for all n greater than or equal to n. Okay? So that's convergence. That's convergence. Okay. So there are several other examples that you can look up in literature. We want to introduce some other concepts in metric spaces. I want to introduce some other concepts. Okay, that's fine. I need to share a new slide so we can proceed. For a sequence, we need to talk about what we call the limit point or the cluster point of a sequence. Cluster points. Cluster point of a sequence. So cluster point of a sequence. Let Xn be a sequence. Let Xn be a sequence. Be a sequence contained, okay, in a metric space S, comma, rho, a point X of the metric space is called a cluster point of the sequence the sequence is labeled Xn. Of course, the entire natural number system in the sequence is a cluster point if for every I want to share new slides to continue that definition. If for every real number epsilon greater than 0 and every positive integer n, there exists an integer, call it n naught. This n naught is greater than n, such that all the terms of the sequence onward will be contained in that sequence. And it will be contained xn naught 1 is for every n naught greater than n, xn naught will be in a ball, an open ball centered on x with radius epsilon. Okay? So in other words, what we are trying to say, look at this is just the summary of the definition. What we are trying to say is that X is a cluster point of this sequence if and only if every open ball centered on what you call the cluster point X with radius R. Of course, radius R here is epsilon. Okay. You have infinitely many terms of the sequence, okay, inside this ball. Okay. Infinite. These are the terms of the sequence. X naught. Every n naught. Remember, n is known. N could be 10, n could be 100. But this one is infinite. And every number after that, that's like n plus 1, n plus 1, that qualifies to be n naught, n plus 2, n plus 3, up to infinity. All this from here to here is infinite. All of them, all the terms of the sequence, like x n naught, like x n plus 1 is in the ball. Okay, xn plus 2, xn plus 2 is also in the ball. Okay, xn plus 1 million is also in the ball, So all the terms of the sequence, as n becomes extremely large, they are all of them are in the ball. The ones that will be outside the ball will be finite. That's the ones that may be outside, will be possibly the ones less than n. For instance, x n minus 1, okay, may not be in the ball, possibly may not be in the ball, okay, but we can count them. We can count them. The one that are outside the ball are finite. The at most you have of them is n of them. So in such a case, this convergence, this what we call the cluster points or the limit points or the accumulation points. Okay, so all these terminologies, they mean one and the same. And of course, I remember one of the exam we wrote while we were in school. Very simple question there, but many people failed it. The question was, what's the difference between the difference between the difference between limit point, cluster point, and accumulation point. Ruben, what's the difference between these three? Or Sadiq, anybody? What's the difference between limit points of a sequence, cluster point of a sequence, and the accumulation point of a sequence? What's the difference?
Hello, Prof.
Yeah, I said, what's the difference
Yeah, it's
between
this five.
point?
So let me say
You said
something about the difference between limit point and the cluster point.
that the difference between the
Li-
limit point of a sequence, the cluster point of a sequence, and the accumulation point of a sequence. So what's the difference?
yeah, the limit point is may or may not it may not be in the sequence itself, just parts of our set.
Okay.
But when the cluster point is a member of the given sequence. I think cluster point and accumulation point are the same according to me.
Okay, cluster point and accumulation are the same. I think that opinion is that of, right? Uh, Ruben, have you said anything? I've not heard you. I think that's
Is
Seti that
is my
spoke.
bottle?
You said?
I'm Sage. Is my bottle was talking?
Yes, I know. I'm talking of Ruben now. I am looking for your own opinion. Ruben is silent. I hope Ruben is not sleeping. Okay, I wanted everybody to talk. Okay, but meanwhile, it's the same. Limit point is the same as cluster point, is the same as accumulation point. This is the same thing. So sometimes we say the limit point of it is still the same thing as the cluster point. It's also the same thing as the accumulation. So they are one and the same. There's no difference between them. And as I said, I remember that exam vividly. Very simple question like this, but many people didn't get the correct answer. Okay, so we are going to look at some theorems. Are going to look at some theorems. Um, theorem. a point X of a metric space X comma D, S comma rho is a cluster point. It's a cluster point of a sequence The sequence is of Xn. Okay, if and only if and only if there exists a subsequence which you can call xnk. Of course, the terms is counting from k equal to 1 to infinity. This subsequence is of xn, subsequence snk of xn. Okay, such that snk converges to the accumulation point x, and this will happen as k becomes extremely large, as k goes to infinity. Okay. That theory, I want you to just look at the hypothesis slowly and digest it and possibly make a sense of what that theory is saying. It's talking of x being x, of course, a point of a metric space. For x to be a cluster point or a limit point or an accumulation point of a sequence xn, that will happen if and only if there exists a subsequence xnk of xn. So this sequence is of this, subsequence of this, such that the subsequence will converge to the limit of xn. Okay? To converge to the limit of xn as k goes to infinity. Okay, so let me show you how to construct the proof. The proof is a necessary and sufficient one, so meaning that you have two parts. If you want to construct the proof, you have the necessary part. Okay, in that one, you suppose that x is a cluster point. S is a cluster point. S is a cluster point of the sequence xn. Okay. So if you let n1 be the smallest subscript among the n's, such that you have that the sequence xn belongs to B1x. You know, here the radius is 1 and the center is on 0, so meaning that you've taken the radius epsilon to be 1. Okay. Now, if you examine the collection of all subscripts, examine the collection of all subscripts of terms of the sequence I share the next slide. Okay. If you take, for instance, if you take epsilon to be half and repeat the process, you find that N1 is N2 is greater than N1. Of course, where N2 is the smallest subscript, term in B half X. So if you continue this procedure, you discover that you construct a sequence of balls like Xn, in which X, N, K plus 1 and above, all of them, all your XM of this nature, if you call it XM, will all lie in B 1 over with radius K plus 1 X. And of course, you know that X is the cluster point. So you now see that by induction, you have that X and K will be inside the ball B 1 over K with radius X. So that ends the proof on the necessity part. Okay, the sufficient part, you can also similarly argue in that sense. Okay, so that will now lead us to Cauchy sequences. Cauchy sequences in metric space. I'm sure you know, fundamentally, one of the class of sequence that is essential in establishing convergence is Cauchy sequences. And we studied Cauchy sequences in reanalysis. So we also have such a sequence, our slides, so we can proceed. Share a new slide so we can proceed to that subtopic, Cauchy sequences. Okay, Cauchy sequences. Okay, of course, like we usually do, the first one will be definition. A sequence Xn, of course, the natural number system entire is the domain of points of a metric space S, rho is a Cauchy sequence. It's a Cauchy sequence, or is called Cauchy if for any real number any real number, epsilon greater than 0, there exists a particular natural number, n naught, such that for all nm greater than this n naught, you have that the distance between succeeding terms can never exceed epsilon. The distance is the metric rho of xn, xm, all of them, all the terms above n naught, all of them, the distance between them, xn and xm, all of them will never exceed epsilon. In other words, I can put all the terms of this sequence inside this ball. This is a ball, I'm sure you know. This is an abstract ball. So I can, an open ball in particular. So I can put all the terms of the sequence inside this ball with radius epsilon. Okay, the terms outside the ball, these are succeeding terms. I'm sure you know that. In other words, n is greater than m. Okay, so you're talking of terms of sequence like x, n, the distance between xn and xn plus 1. No, something like this. You know, succeeding terms. I'm sure you know that because n and m is such that m is greater than n. So we are looking at the distance between succeeding terms can never, all of them will be put inside this board. Okay? So if that happens, we say that you have a Cauchy sequence. Okay? And of course, we've been studying Cauchy sequences so much. So many of those results, we are going to visit them or repeat them if you like. So let me share another slide. Then we see some of the results, or we recall some of the results. Okay? Theorem. Theorem. Every convergent sequence Xn in any metric space S, rho is Cauchy. So every convergent sequence, of course, just pick the fact that the sequence is convergent, you can show Cauchy. The converse of this theory may not necessarily hold. In other words, every Cauchy sequence may not necessarily be convergent. Maybe as we go on, you will see that. The proof is very simple to prove. Okay, all you need to do is say let xm be convergent, and then you use triangle inequality, and then your job is done. Very simple. Well, let me share a new slide. Just remember the hypothesis of the theory. Every convergent sequence xn in any metric space is Cauchy. Okay, so once you remember what it means for a sequence to be convergent, your job is almost half done. So let me share a new slide, and then we proceed from there. And I want you people to contribute as I'm proving this. If I say xn is convergent, for instance, I say let xn, okay, the sequence with the natural number system be the domain. Let that converge to a limit, let's say x, for example. What does that mean? What does that mean?
Even epsilon naught greater than
What does
0?
that mean? Yeah, it means that if I have given epsilon greater than 0,
There
okay,
exists
there exists a
n
particular natural number n, yeah,
yeah.
which may depend on epsilon, such that for all n greater than that n,
absolute value of
the modulo. You are in a metric space of xn
x
and what you claim to be the limit, is it not?
is less than
Is
epsilon.
less than epsilon. This is what you mean by convergence now, is it not? Is it not?
Yes, sir.
So in other words, you want to find there exists. This is always the job. This is always your duty. You want to find this n epsilon. So for our case, particularly for our proof, particularly, we want to find, let's call it n naught. Okay, we want to find n naught such that the rho of xn xm, okay, is less than epsilon. Okay, for all n m greater than what? N naught. So that's my job. I want to find this n naught. Okay, I share a new slide and we continue the process. Okay. Now, since xn converges, Sn converges to x as n goes to infinity, what that means is that given epsilon greater than 0, that there exists n greater than 0 such that the rho of xn and x is less than epsilon over 2 for all n greater than n. Am I correct to say that? Am I correct to say that? And this will happen for, of course, also for any other integer, greater than n, this will also hold. This inequality will also hold. So for any
any
m
greater than
greater than n, it follows that
rho of
the rho
xm
of
minus
xm comma x,
less than
right,
epsilon.
is also less than epsilon over 2. Is it not? Aha. So having established 1 and 2, if you call this equation 1, call this equation 2. Having established 1 and 2, you now see that by triangle inequality, because we are in a metric space, I'm sure you remember, in metric spaces, triangle inequality is one of the axioms that are satisfied, right? Right. So by triangle inequality, I have the following. What I'm looking for, which is actually rho xn xm, okay, is less than or equal to, by triangle inequalities, less than or equal to xn comma x plus rho x comma xm. Do you understand that? We know this candidate is less than epsilon over 2 plus, that's equation 1. This one also is less than epsilon over 2. Is it not? Number 2 equation. Is it not? Which epsilon over 2 plus epsilon over 2 is epsilon. In other words, we have shown that this is less than epsilon. What's the meaning? Hence, we've just shown that the sequence xn is Cauchy. Because this is the definition of Cauchy. Okay? You just shown that. You started with the fact that the sequence is convergent. You ended up by showing that the sequence is Cauchy. So every convergent sequence is what? Cauchy. Okay? Let me give one more result, and then we can proceed from there. Another theorem. Another theorem. Let S, rho be the real line with the usual metric. Then a sequence xn is Cauchy in R if and only if it converges. It converges in R. Okay? So that obviously you can simply do the proof of that. Okay, so let's define yet another concept of boundedness in metric spaces. Definition. This definition has to do with boundedness. Definition. Let X, rho be an arbitrarily metric space, and let's Xn be a sequence contained, I think somebody's contained in X. Then the sequence Xn is said to be bounded. If there exists a particular R, a real number greater than 0, such that you have that all the terms of the sequence will be inside a closed ball with that real number as the radius of the ball. Is a closed ball. I'm sure you remember a closed ball centered on 0. And this will happen for all n greater than or equal to 1. That's for all the terms of the sequence. All the terms of the sequence can be put inside this closed ball with radius r and center 0. Okay? Where 0 is any point in X. Of course, this 0 is not the 0. You know, you are in a metric space. Okay? So the 0 is any point in metric space. And BR0 denotes the closed ball centered at 0 with radius r greater than 0. So that's boundedness. Of course, you remember boundedness in R, in real numbers, in R. When you say that a sequence is bounded in R, that's in real analysis. You are simply saying that there exists a K greater than 0, such that the modulus of xn is less than, okay, or equal to k. Is it not? For all n in n. Okay, so this ball, closed ball, is this one in metric spaces with radius r. Your k here translates to the radius r centered on 0. So you are talking of a closed ball that will contain all the terms of the sequence, all of them, for all n greater than or equal to this. No particular term will not be inside this ball. Not even a single term of the sequence, okay, that will not be inside this closed ball. If you find just one term of the sequence that is not inside this closed ball, then the sequence cannot be bounded. Sequence is not bounded. So this all the terms of the sequence must be inside this closed ball for us to claim that the fact that, or justify the fact that Xn is a bounded sequence. Okay, so you now see the translation of boundedness in a metric space, just
Yeah,
like
it's
we
okay.
had in reanalysis.
It's okay. No, yeah, over here. Yeah.
Somebody is
Thank you.
Someone is talking.
Have a good night.
Who is that? Maybe the talking is not for us. I think that's Sadiq. Sadiq, please mute yourself. Mute yourself, Sadiq. Okay, so okay, that's fine. Please just a second, a minute rather. Okay, so we just define boundedness, so we can now proceed with some other results. Has to do with boundedness. Okay, so that's fine. Theorem. Theorem. Let S, rho be an arbitrary metric space, and let Xn be a Cauchy sequence in X, then Xn is bounded. Xn is bounded. I'm sure you know that. If you have any metric space and you have Xn, a Cauchy sequence, okay? A Cauchy sequence in that metric space, X, that Cauchy sequence is bounded. Okay? So I'm sure you can, the proof also can easily be justified. You already know the class of sequences that are Cauchy. Okay? That's you have rho Xn, Xm, okay, less than epsilon. This is for all n, m greater than your n. And of course, you know that m obviously may be greater than n. So these type of sequences can be put inside BR0 closed. So it's bounded. You can do that. Can justify such a proof. Okay. So we now want to go to next chapter. The last chapter that I'll be looking at in metric spaces, which has to do with completeness in metric spaces. By next lesson, we now go to chapters that has to do with non-linear spaces. That's linear mappings in non-linear spaces. From there, we begin to look at other topics in non-linear spaces. And lastly, we end up with Hilbert spaces. Hilbert spaces will be the last topics we'll be looking at in functional analysis. Obviously, in Hilbert spaces, a lot of optimization is being done, and I'm sure many of you that are aspiring to, have some graduate courses in or research in finance or thereabouts, you cannot escape optimization tools, which you have in Hilbert spaces. So today we'll be rounding up topics in metric spaces, which are the introductory part of functional analysis. It's okay. So I look at this topic, completeness in metric spaces. In metric spaces, completeness. What do we mean by saying a space or a metric space is complete? What's the meaning of that? Well, let's define that. Let Xn or X comma rho be a metric space. Be a metric space. The space X comma rho, then S comma rho is said to be complete. So that word complete is a term. It's a concept. Said to be complete or is called a complete metric space if every, I underline that word, every. If every Cauchy sequence, if every Cauchy sequence in the space, which is X, converges to a point of the space, converges to a point of the space, a point, if you like, a point of the space. What's the space? X. Okay. I'm going to share another slide too, but look at it. I will still explain it more and more because you must understand the concept. A space is said to be complete. That's a complete metric space. Is a metric space in which every Cauchy sequence in that space converges to a point of the space. In other words, for a space to be incomplete, you have a Cauchy sequence in the space, but the limit point of the Cauchy sequence is not in X, is not in the space under consideration. That becomes incomplete. Okay? Let me share a new slide to demonstrate or to illustrate what I mean. What I'm saying is this. If you are saying that a space is complete, you are saying that that's the key word, every Cauchy sequence, okay? That Cauchy sequence will normally, you can say Xn, converges to X star. Let's say X star is the limit. And this X star must be inside the space X. Okay? That's it. The limit of the Cauchy sequence must be inside the space. That's completeness. But perhaps if you find Xn such that Xn converges to X, for example, and X is not in X, it then means that this one is complete metric space why this one is not complete or incomplete. Incomplete matrix space. Okay. So you see that Cauchy sequences are very important. That's why I told you that Cauchy sequences are fundamental sequences. You see, we use Cauchy sequences to characterize spaces, including a matrix space, such that every space, every matrix space in which every Cauchy sequence converges is complete. And if you find a space which you can even pick just one Cauchy sequence and it doesn't converge, then that space is not complete. Okay, for example, look at this common example we have been given. If you have this 1 over n sequence, 1 over n, look at this space, 0, comma, this space, 0, comma 1. Okay, this space, this Cauchy sequence is here, obviously. Okay, is here. This Cauchy sequence, but it converges to 0, right? Is 0 under this space? Is 0 in X? Is 0 in X? That's my question.
No.
This sequence is there, but the limit converges to 0. Is 0 in this space? It's not there.
No.
0,
Yeah,
because
it's not
0
complete.
here is not there. Yeah. So you now see that this space is not complete. It's not complete. Okay, you picked up a Cauchy sequence there, but the limit is not in the space under consideration. So it's not complete. Let's look at some results as well. I'll share some slides. Okay. Well, this theory has to do with subsets of complete matrix spaces. What becomes of them? Theorem. A closed subset, of a complete metric space is also a complete metric space. So what that means is that the space is a complete metric space, and Y is closed. If Y is a closed subspace, Y is a closed subset of X, then Y is complete. Let me share another slide to demonstrate that. A closed subset of a complete metric space is complete on its own right. It's a complete metric space on its own right. That's what that theory is saying. Let me share a new slide to illustrate that. What it's saying is that, of course, the X comma rho, that's the entire space, and is complete. If you now have a subset of it, which is Y, a subset of X, such that Y is closed. Y is closed. Then if that is the case, and we are saying that Y comma rho is a complete metric space on its own right. It's a complete metric space. Okay? I'm sure you know that Y is a subset. Y is a subset. Y is a subset of X. Okay. This is like row Y. This is like X comma row. Why this one contains Y comma, if you like, row Y. Okay. So if this one is complete and this one is closed, then this one is also a complete metric space. Okay. So that is that result. We are just trying to recall some of all of those results. Okay. Yet another result. Theorem. Let X comma row be a metric space, not necessarily complete, and let Y be a subset of X, which is complete. Let me find out, have I given you people any book on this course on functional analysis? Have I given you any book on it? I don't think so. I think the one I gave you book was on metric space. So I'm going to share a book to Mr. Yomi, so to distribute to all of you. So I will give out a book maybe later in the day for this course. I think the one I gave was
Not yet, Prof.
on reanalysis. Yes, I'm going to send a book across. Okay. So Y is a subset of X, a subset of S, which you have X comma row be a metric space, and that metric space is not necessarily complete, and you let Y be a subset of X, which is complete, complete metric space. So I missed out complete, which is complete metric space. Then Y is closed in X. Y is closed in X. What does that mean? What does that mean? We're saying that a complete subset of any metric space is closed. A complete subset of any metric space is closed. So that's what that result you have. So if you are in a complete you have a Y, a subset of X, which is complete, then Y is closed. So a complete subset of a matrix of a complete subset of any metric space is closed. Okay, so that's what that result have. We go straight to one of the famous theories that is very important in functional analysis. This theory is called the contraction mapping principle. And of course, is closely connected with the fixed point theory. Now, this theory is one of the most applied theory in analysis. Okay, that's in mathematics and engineering, in physical sciences as a whole. And it involves a method in which you use to solve some problems, physical problems involving models, models in science, in management, and so on. If you are in finance, in economics, and so on, you're going to have virtually most of the problems you solve relating to maths are mathematical models. And once you have a model, well, one of the challenges, how do I solve the model? How do I solve to get the solution? Such model may involve maybe fractional differential equation, maybe partial differential equation, maybe ordinary differential, or even integral equation. How do you solve those models? Of course, literature is filled up with methods, And one of the very important and powerful methods that is highly efficient compared to other methods is the fixed point theory method. And this this fixed point theory method is rooted in the theory that we want to establish now, which we call the contraction mapping principle. So let me just state it, and possibly we end up by giving you stating what we mean by the fixed point of a set. So let's talk about the contraction map. Contraction mapping principle. Okay, what do you even mean by a contraction map? Okay, a mapping F from a metric space X to X is called a strict contraction, or simply a contraction. Okay, if there exists a constant k in 0, 1, excluding 1, it includes 0 but excludes 1, such that the distance between f of x and f of y, x and y are elements in the domain. Okay, f of x, f of y is less than or equal to k rho of x comma y. Rho k, k rho of x comma y. So that's contraction. You can see what contraction does. Contraction shrinks the distance between images compared with the distance between the elements from the originating, from the domain. In other words, if I have, let me geometrically, let me share a new slide to show you what I mean or what contraction is saying. Okay. Of course, you have, this is my X at the domain F. Mapping, this is F, mapping the S to here. F applies, you have X, Y, applies here, you have rho X. Sorry, you have F of X rather. F of X, F of Y. X and Y are elements in the domain. When F applies to them, you have the image of X, F under X, that's F of X. Image of F under Y, that's F of Y. So if you look at the distance between here, and the distance between F of X and F of Y, what contraction is saying is that there exists a k between 0, 1, such that the distance between F of X and F of X and F of Y, okay, will be less than or equal to k distance between x and y. So what a construction map does is to shrink the distance between the images and between the objects and the images will be shrunk. So that's exactly what a contraction does. Okay? Or if you like, if you have draw it more, you now see that the distance between here is wider. That's between x and y. Now, but when you come to the domain here, the distance is reduced. This is f of x, and f of y. So it shrinks, the distance is reduced here, while the distance is longer. So a construction map, f, shrinks the distance from domain and shrinks it in the codomain. Okay, so now of course there are results involving the contraction map. One of such results theorem is that every contraction map is continuous. In fact, every Lipschitz map is continuous in a general term. So every contraction map is continuous. You can always prove that. I'm sure you remember the definition of continuity in metric spaces. Do you remember? So let F from X row to X row be a contraction. What does that mean? What that simply means is that there exists a k in 0, 1, in 0, 1, such that row f of x, f of y, okay, is less than or equal to k row of x, y. Okay, that's the meaning of that. Okay, now, and that will happen for every x, y in the domain x. Of course, if you let epsilon to be greater than 0, okay, you want to find, a delta greater than 0, talking about continuity now, such that row x, y less than delta implies that row f of x, f of y is less than epsilon. That's actually, if you can find this delta, your job is done, such that row x, y, that distance between x and y is less than delta, implies that distance between f of x and f of y is less than epsilon. Okay, but already for contraction map, we already have all of this. So with that, you can always compute a delta. So let's do that, and as follows. Okay. So since rho is a contraction map, if you choose, you have the choice, of course, to do so. So if you choose epsilon to be equal to delta, then you now have that rule f of x, f of y is less than or equal to k rule of x comma y. K rule of x comma y. Okay? Now, the whole of this now is less than, we have already said that epsilon can be equal to delta. Okay? So, and this rule xy is less than delta. Okay? So, you now discover that the whole of this now is less than k. When this one is less than delta, so this is k delta. And of course, we have said that this is equal to what? This is equal to delta and epsilon is the same. So this is k. Instead of delta, I'll write epsilon because delta and epsilon is the same. And of course, k is a number. K is a number between 0 and 1, not exactly 1. So what's the relationship? And epsilon, so this will be less than epsilon. Okay? Since k is not even up to 1, k is less than 1. Okay? And what's the meaning of that? You have just shown that f, this implies that f is continuous. F is continuous. So every contraction map is actually continuous.
No problem.
Okay, so let me, yes, go ahead.
I don't get well the second line. So how rho of f? Oh, sorry,
Which
it's
of
from
the
the
line?
contradiction.
Is it this one? Okay. Yeah, it's from the contraction, yeah. Because the F is a contraction map. So, and K is from 0, 1, right? So because F is so K is coming from the contraction. That's where we got it from. Okay, so thank you very much. We now proceed to the theory that I'm saying that is highly applicable, and that has to do with the contraction map. Theorem. Theorem. This theorem is called the contraction mapping principle. Other author call it Banach contraction principle. So anyone, or Banach contraction map principle. Okay. So let x comma rho. Let s comma rho be a complete metric space. Then every contraction mapping, f from x to x of x dot. Hello? Hello? Yes. Yes. Yeah. Okay. Okay, what about Jose Horabi? Okay, don't. Have to do. Don't worry. Don't worry, Nga. I told you everything will be all right. I will contact him. Okay, so sorry for that interruption. So F, a contraction, okay, from X to X into itself is a self-map. So into itself, a self-map has a unique fixed point. And as a matter of fact, this theory gives us the method of approximating the fixed point. But then we've not even defined what a fixed point is. Has a unique fixed point. I think we have not defined what a fixed point is. I'm going to define that now. Okay. The fixed point of a map, let me do it here. I don't want to claim this, so that a point X in X is called a fixed point, a fixed point if f of x is equal to x. If f of x is equal to x for some x, this is for some x in x, not for all x. So that's why it's not an identity map, neither is it a constant map. So a fixed point is just for some x. In fact, there are even some map that has no fixed point. So f of x is equal to x, okay, for some x in the domain of x. So this is a fixed point. And when the fixed point is unique, what is telling you that it has at most one. There's not more than one fixed point of this map. Now, what this fixed point, unique fixed point is telling you, or will translate to, has to do with unique solutions. I'm sure you know, for some of you that have solved some differential equation or partial differential equations, ODEs, there are some differential equations and all of those that do not have unique solutions. So, but what this method does gives to us is the uniqueness, not only a method of finding the solution, but the uniqueness of the solution. We are going to explore this method further. Maybe I intend towards the end of the course or the whole of course to just come up with one model, maybe involving finance and so on. When I'll be rounding up generally, I'm going to kind of do a kind of, if you like, a minor kind of introduction to research for you to see that all that we've learned in reanalysis, function analysis, measure theory are actually tools for your finance and your economics and all those. So obviously we pick up a model involving differential equations and or PDEs or even fractional differential equations, and we see how we can apply, especially this method, this contraction matching principle, which is highly applicable in solving them. So that will be our lecture today. And I want to, from the information reaching me,